Welcome to Challenging Climate, a podcast where we discuss the science, technology, and politics of climate change. I'm Pete Irvin, a climate scientist.
And I'm Jesse Reynolds, an environmental policy expert. Each episode, we bring on a guest with a unique perspective and deep expertise on climate change and put challenging questions to them.
In this episode, we spoke with Dr. Erica Thompson, a senior policy fellow in the ethics of modelling and simulation at the London School of Economics Data Science Institute. In this episode, we discuss Erica's recent book, Escape from Model Land, which considers how we can use mathematical and computational modelling to inform real-world decision-making without becoming lost in our assumptions.
Over the recent decades, policymaking and other major decisions have become increasingly based on complex models. The economy is an obvious example. In the last few years, how to manage the COVID pandemic really brought modeling to the fore. And of course, in our area of expertise and area of focus on this show, we talk about climate change, where models are, of course, central. Thompson's book really confronts the challenges that reliance on such complex models can pose, and importantly, how to avoid the pitfalls.
Yeah, and I think in our conversation, and in her book, Erica brings up a few things that are really important to bear in mind, and I think are really useful ideas. The idea of models as metaphors for the system they represent, and what she calls model land, the space in which our models' assumptions are true, and many models are very useful, but they make assumptions. And when you apply them to real-world problems, they don't always come true. So her title, Escape from Model Land, is about making that transition out of the world of assumptions and into the real world. And how can you go about informing real-world decisions and decision makers in a way that responsibly acknowledges and recognizes the limits of your models? There's basically two routes out of Model Land as she presents it. There's a quantitative route, where you basically test your model so many times that you get to be sure how well it works. And this is the case with weather models. We know they work fairly well, and we know their limitations because we've run them thousands and thousands of times and tested them thousands of times. And then there's the qualitative route. How do you test a model of something that takes a very long time to materialize? Like, for example, climate change. It's much more difficult. And a lot of our conversation focuses on those challenges. Yeah, I think understanding models and their use is challenging, but Erica does a great job of explaining that in this conversation, and even in greater depth and in a better way in her new book, Escape from Model Land. So here we are now, our conversation with Erica Thompson. All right, welcome to Challenging Climate, Erica.
Hi, nice to be here.
Well, we met many years ago now, back in Bristol. Yeah, can you tell us a little bit about your origin story? Because you did a PhD and that led you to start questioning models. Could you just give us a little bit of background? What led you to write this book, Escape from Model Land?
Yeah, okay. So an origin story, that sounds a bit sinister. But my background is in maths and physics. And then I did a PhD at the Grantham Institute at Imperial College in London. And that was about North Atlantic storms in a changing climate. So, you can imagine I went and found some models and had a look at the model output and did some analysis. And it was really interesting. I started with my literature review, and there were a whole load of different results in that literature review. And what I sort of began to realize as I was putting everything together was that actually these models completely disagreed with each other. You could find a model saying the storm tracks were going to go north, they were going to go south, they were going to get stronger, they were going to get weaker, frequencies of more intense storms and frequencies of less intense storms. And, a picture was sort of emerging. But at that point, and this is sort of 10 years ago, there really wasn't clear agreement. And the models, what I found most striking was that they were disagreeing kind of outside their own error bars. So I looked at that and said, well, does this really tell me anything about North Atlantic storms? Actually, it's not telling me very much about North Atlantic storms, but it's telling me a huge amount about the way that we as scientists, as a community, are going about constructing these models and the way that we are assigning confidence to them, perhaps unwarrantedly, because obviously you would expect that if you are making estimates of something, you would hope that to begin with, you may have very wide ranges, but you would hope that the error bars would at least overlap. And what I was sort of seeing was that they didn't really overlap. So then that set me off kind of thinking about models, thinking about confidence in models, thinking about how we assess uncertainty and what kind of mathematical methods we use to assess uncertainty. And I've been, for the last 10 years since my PhD, I've been at the London School of Economics, where I've worked in the Centre for the Analysis of Time series and more recently at the LSE Data Science Institute. And I have a program of research there which has looked at, not just climate, but various different kinds of models, thinking about how we have confidence in models, how we assess the levels of uncertainty in model-derived information, and then kind of taking it one step further into the decision process and saying, well, how do we actually use model-derived information to support decision-making? How does that depend on the levels of uncertainty? What kind of methods should we be using? What are the sort of pros and cons of doing it like this or doing it a different way? And so that's been super interesting, And then I should say I've written this book called Escape from Model Land, which is sort of a summary of my explorations in these different areas and my thinking about how we use models and kind of what are the ways that model-derived information kind of propagates through a decision-making process.
So I found your new book to be quite fascinating. I haven't read anything quite like it, so congratulations. From my perspective, I want to start a bit back. Let's start at the basic. And I'm curious, what is a model precisely? I think to the layperson, a model might be, someone who shows clothing or a small car that's smaller, toy train, right? Right? Or a role model, something to look up to. But here we're talking about something different. And as I read your book, I realized, what are the boundaries of a model?
Yeah, I think it's a good question, and the boundaries are probably pretty fuzzy. So, I would say a toy train is a model. Someone who wears clothing is a model because they are making a model of how it will look on you, maybe not a very good model. And so I kind of take a very broad view of what is a model. And a model is essentially a metaphor for how one thing is like another. You create a model which is unlike the real thing in some respects and hopefully like it in some respects, and you use the ways that it is like the real thing to make inferences about the real thing. And so that could be a toy train, it could be somebody wearing clothes, it could be a photograph or a map, or it could be all the way up to a sort of really complex climate model prediction system, which takes in the laws of physics and a whole load of information about the initial state of the system and propagates it forward into projecting or predicting the future state of a system. And so all of those, I would say, are models. But the ones in which I am most interested and which I focus on in my book are the sort of complex models where we are trying to predict something about the future and where we are making extrapolation. And I distinguish that, for example, to distinguish weather models from climate models, because weather models, I would say, are essentially interpolatory in the sense that we have a huge amount of past data and we expect that tomorrow's weather is probably very much like past weather, in the sense that we can calibrate our model based on past data. We can look at how well the weather forecast performed and build up a statistical picture over multiple days, weeks, months, years of testing with the model and with out of sample data. And we can get an idea for how good it is. Whereas when you are taking an extrapolatory view, and so this is where I would distinguish climate from weather, actually we're going quite a lot further forward, to the extent that we don't have past data which is directly relevant, or they could be directly relevant. We hope that the laws of physics will remain the same, but we know that the amount of sea ice in the Arctic is not going to remain the same. So the question of to what degree prior calibration is relevant for future performance comes into play. And so that's also relevant for economic forecasting, for example. We understand that politics is changing. And so the way that the financial markets behaved in the past is useful and informative, but it's not going to give us a perfect prediction of how they behave in future.
So I think I heard in that response 3 layers of models. So at the most general level, there's a metaphor. One thing that represents something else is an approximation that could include clothing models, for example. And then at a higher level of specificity, there are quantitative models. They often have stocks and flows, and they can be in a steady state, and then there can be a perturbation. You can ask the question, if we increase this box or this flow, what's the response? And then a third level that's even more specific is saying, well, let's exclude those models that are more routine and where we're moving into somewhat uncharted territory, which is climate change, which is an economy in which not just politics, but of course also technology, right? So information technology changes the way the world works. And the WTO exists now and it didn't exist 30 years ago, let's say. And maybe COVID as well is another example where there was some uncharted territory as well. So, what can we use such models for? Let's just focus in on these extrapolation models, as you call them. Extrapolation meaning we have the data sort of clustered in this one region, but we're curious what might happen outside of that cluster. So, the extra meaning outside, extrapolation. How can we think about their uses at sort of a high level sense?
Ultimately, we want to use these models to predict some element of what the future is going to be like, or at least to do an if-then analysis. Say, if we do this, what will happen? And if we instead decide to do that, what would happen? And so we're sort of exploring different possible outcomes, not just with the intent of predicting it and making a perfect prediction, but with the intent to choose how we interact with this system in order to influence it. So, we make a model of hospitalizations due to COVID in March 2020, for example, and the aim was not to make a correct forecast. The aim was to support decision-making, policy-making, to avoid a worst-case scenario and to sort of bring that down. And so the aim with these kind of models, I think, is always going to be to intervene on the system, to make some form of intervention, to make decisions, to make policy, to maybe that's climate infrastructure, climate adaptation decision making. Maybe it's whether you are going to build a new hospital or hire extra nurses, or maybe it's about sort of investment decisions on a longer timescale if you're a water company or an infrastructure development company that is making long-term decisions. Then you use models to make these decisions and to help you to think about what the future is going to look like and to help you compare and counterbalance different possible scenarios and to just think through how and why you might act and what the possible outcomes might be and how they matter to you.
So, coming to the title of your book, what is or where is model land, and why should we think about escaping from it?
So model land is what I like to think of as where you are when you are inside your model. If you're inside your computer, or if you've written down some equations and you're working through the logical consistency of what things are like when you assume that all of your numbers are correct, all of your equations are perfect, all of your assumptions are true, everything works, then you're inside model land. And when you're in model land, your statistical methods can work perfectly. You can make statements about the future. You can make predictions, projections without any uncertainty. And so the question then is, to what extent should I believe that things within the model tell me anything whatsoever about the real world? Because I'm not interested in the model. I don't care what the model does. Nobody cares what your model does. They want to know what's going to happen in the real world, and they want to inform decisions that are going to be made in the real world. And so by escaping from model land, I mean finding that bridge between what your either mathematical or conceptual or whatever picture looks like inside the model, to be able to transform that into a statement about reality, real life.
So much of your book and much of our conversation will highlight the challenges and sometimes the shortcomings of reliance on models, especially these complex extrapolating ones in decision making. But before we get into those challenges, I want to ask you about the side of the glass that's half full. Where have models been relatively useful and successful? Where have humanity and decision makers benefited from complex models?
I mean, models have been incredibly successful, and we only have to look around us at our sort of computational infrastructure and our cars and our lives, and the public transport system and the internet and absolutely everything. The world runs on models, and for the most part, they work extremely well. In particular, the models which are founded on a huge amount of data and where we expect that tomorrow will be quite like today, those models can do extremely well. And where they don't do well, we actually have a pretty good understanding of when and where they are not going to do well. So, for example, the weather forecast. When you take your phone out of your pocket and take a look at the weather forecast for tomorrow, you have a pretty good understanding of what the quality of that weather forecast is likely to be, how often it's likely to be right and how often it's likely to be wrong. And you can use that to help you understand whether or not to trust it to make a decision. And that tomorrow's weather forecast is pretty good. That the weather forecast for 3 or 4 days' time is okay. and you don't even look at the weather forecast for 3 weeks' time because you know that it contains only marginal information. So it's not worth the effort. So you have a good understanding of when and where you can use that model. And so we have loads of models in our lives that are somewhat like the weather forecast, and they are incredibly helpful in making decisions from the personal to the national and the international every day. And so certainly, in reading my book, there is a degree of skepticism about some aspects of modeling, but I hope one of the messages that I'm really clear on is that we need to not throw the baby out with the bathwater, and that actually, we need to be building on the successes of models in certain contexts to ensure that we make best use of them in these other contexts as well.
So is it a correct interpretation if I were to say that although I find Escape from Model Land to be a wonderful title for a book, it's provocative and it, of course, brings to mind, movies and stories and so forth, that really what you're getting at, the main message is that it's important to maintain an exit path, an exit ramp, if you will, not necessarily take it, but maintain a bridge, I think is the term you used a moment ago, and know when it's right to take it. Is that a reasonable interpretation?
Well, no, we always take it. I mean, in any case where you are using model-derived information to support decision-making in the real world, then you have escaped from model land because you are living in the real world. But the question is how you support that. Do you support it with reference to a large archive of past data and past forecasts, which you're able to robustly evaluate using statistical methods? Or is it the case that actually the escape from model land is mostly mediated by expert judgment rather than by statistics of past data, in which case we need to be somewhat more careful about it? That's the distinction I would make. I say we are always living in real life. You cannot live inside your computer.
Yeah, and so on escaping from model land, I think you just mentioned there, there's two tests or two approaches. There's a quantitative route where, you've got lots of tests that have been made on weather models, and you can test your new model on 1,000 past occurrences and get a good sense of how well it works. And there's other situations where you can. And I think we're going to sort of split that into two halves, because I think in some cases you've got well-defined problems, and in other cases, you've got less well-defined problems, or where the framing of the problem is up for grabs. So starting on the well-defined side and staying in climate, how do we go about answering questions like, what's the probability of another really extreme heat wave like the one we saw in Lytton in Canada last year?
Yeah. Okay, so that's something where we are sort of on the borders, I think, between the quantitative exit, having the quantitative exit from model land available and having to rely on the qualitative. And so we do a bit of both. So, we can say, what are the statistics of past heat waves? And we can look at that. We can analyze that in detail. There are plenty of papers about that. And then you can say, actually, because the climate is changing, the underlying dynamics of this situation, we expect to be different in the future than how they were in the past. And therefore, we can't fully rely on past statistics. And so maybe we need to do some complex modeling of the dynamics. And so we resort to climate models. We take up our climate model and we say, if we run this with more CO2 in the atmosphere, then what are the statistics of this kind of heat wave? And so you can do that. Then you have all sorts of complexities. So, we are not in a steady state at a certain amount of CO2 in the atmosphere. We're on a transient. So how do you decide what your class of models, which are sufficiently similar to the Earth in 2022, what do we consider to be representative? And how many times are we going to run it? And how are we going to generate the initial conditions or the ensemble of forecasts that we might use in order to generate some statistics? And then there's a question of how you do the statistics. I mean, for example, you picked a particular extreme event, and that is a cherry picking in itself, that if you start your statistical analysis immediately after a particularly extreme event has been observed, then you should expect to see something that looks rather different to how it might look if you had done it before the extreme event had happened. But of course, there's nothing to particularly make you decide to do that. So the statistics become difficult, right? It becomes contaminated by your choice about what to investigate. And so that's something else that I sort of bring up in the book, is that actually, because we are constantly, as scientists, making decisions about our priorities and our level of interest in different kinds of events and what we think we need to investigate, because it has social value. We would like to investigate the recurrence time of a heat wave in Canada because it happened and because it was particularly damaging and it was a particularly dramatic event. But by choosing to do that, we are sort of biasing the statistics.
So I think climate models might be at the pinnacle of model complexity or approaching the pinnacle of model complexity because they're these models that work of many, many hands, 20, 30, 40 people perhaps working on it over the course of many, many years. They put them on these supercomputers that basically hog up the whole supercomputer, the brand new supercomputer for months and months and months to run them. Can you describe the models that we use for climate change? What's their character? How do they compare to some of the other models that people might be more familiar with?
Well, I mean, it depends what kind of model you're familiar with. And people might be familiar with an Excel spreadsheet, or they might be familiar with a set of equations on a piece of paper, or they might have experience coding in Python or, doing something fancy in Fortran or one of the more archaic languages like climate models tend to be written on. But climate models have got a sort of dynamical core of the basic fluid dynamic equations for what goes on in the atmosphere and maybe the ocean as well. And then everything sort of goes out from there, and you add subroutines upon subroutines to describe different aspects and different elements of the system. And you can couple those in different ways and improve the resolution. And so, it's sort of never ending. You can always continue to improve your representation of different processes because there are processes acting at all scales in our climate system, from the large scale thermodynamics of the atmosphere and the greenhouse effect, all the way down to the microphysics of what goes on in clouds and chemical reactions in the atmosphere. So there's sort of no limit to it. And so, as you say, it is limited by the amount of computing power that we have available, and it sort of expands to fill up the amount of computing power that we have available.
One of the thoughts I have on because there's some models where we can quite easily get our heads around them and we can potentially run them 1,000 times and just fully capture their behavior. That isn't the case with climate models. They're effectively, when we think about them, we have, I guess, in some sense, our own internal models of the ideas that drive them and their character. But we aren't creating these sort of miniature virtual worlds that we can't fully explore. This is it's a bit of a different challenge, right?
Yeah, it's a tricky one. I mean, and then sort of statistically, you might say, well, I would like to fully explore the sensitivity of the model to changes in parameters, and that will be a way of getting a grip on the uncertainty that we have. But of course, if we do that, we're still acting in model land. When we generate a sensitivity analysis of the model, even if we could actually do that, which we can't because there are vastly too many parameters and varying all of them would take probably longer than the lifetime of the universe to calculate and to run simulations for each of them, because you have this curse of dimensionality. When you multiply up dimensions, you have to do it in every dimension every time for every other dimension. And so sort of statistically, we might like to be able to vary the parameters and generate some sort of uncertainty distribution. But actually, if you think about the question then of escaping from model land, what is it that these variable parameter runs of a model tell you? They don't tell you anything necessarily about the real world. They tell you about the properties of your model. And so actually, when you start using statistical methods like that, you're making a very strong assumption about the escape from model land. You're saying that the dynamical properties of my model under this sort of parallel universe assumption that any value of the parameters is equally likely, or maybe I put some sort of distribution on the possible values of the parameters and propagate those through, then you're making really quite an extremely strong and rather strange assumption about what that means for reality, which obviously we live in one universe, not multiple parallel universes.
Staying on the topic of climate change, what do you see as the greatest challenges to modeling that are specific to climate change, or at least more serious in the case of climate modeling?
It's a good question. I guess I think that one of the challenges that exists is how to create and defend probability distributions about the future, because it seems that what decision makers want, or at least what the IPCC thinks it ought to be giving to decision makers, is probability distributions of future climate given different scenarios of emissions and such like. And so if we want to be able to take multiple models and turn that into a probability distribution, I think then we run into this question of escaping from model land extremely quickly, because you could say, well, okay, I've got 20 different models and they've been generated by people in different contributing institutions, in the UK, in the US, in France, everywhere, multiple institutions around the world, and they've contributed these. But if we turn that directly into a probability distribution, then we are ignoring all of the non-independence between them. They are constructed from the same foundational principles, often by the same people, often using the same subroutines. They're run basically in the same sort of way. And so when you take those, you can't take 20 models to be 20 independent throws at a dartboard. And so this really changes the statistical paradigm for interpreting that ensemble of models. And then you run into questions about, should we weight them equally, or should we say that we're going to weight one model more than the others because it has a better representation of past events or climate history, or maybe it does particularly well on something that we're particularly interested in. And then you just have a huge can of worms of how you do that and how you make those decisions. And do you do it separately for every different circumstance that you're interested in and every statement that you want to make? That's really difficult. And then the further question is actually, what about the possibility that these models don't represent an independent, identically distributed draw from some underlying estimate of what the truth is? And then you run into the problem that the IPCC have had, which is, maybe you have a 90% confidence interval for your model output, say change in temperature in 2100, given a RCP 6 scenario, whatever. And it gives you a 90% interval for the next model run. And you say, actually, I'm not interested in the next model run. I want to know what the real world is going to do. And so the IPCC's previous approach has been to in a somewhat ad hoc manner, just downgrade that probability level of confidence from very likely, which is what would be implied by the 90% distribution, and to say, actually, this is a likely range, meaning a 66% probability of the real world's value falling into that interval. And so it takes a while to kind of wrap your head around it. And I definitely recommend drawing a little normal distribution and putting the bars on and thinking about it. But taking that 90% interval of model runs and calling it very likely means that you have essentially reassigned 24% of the probability mass from inside the range to outside the range. And the IPCC don't define exactly how they do that. And so I think this is really fertile area for then thinking about, actually, what does that mean? What are the consequences of that? So, because 24% of the probability mass is a very significant amount.
I've heard some concerns around the use of climate models, and maybe these are outside of model land, but I suppose it's how the public and the media and decision makers outside of model land are using the information that they get from models via modelers. And I've heard the critique, and I'm sympathetic with it to some degree, that the models in climate change are somewhat reified, that they're put up on a pedestal. The mantra of those who are more on the activist spectrum say, listen to the science. Yet the science is speculative. I mean, we know about energy balances and so forth, but as your book describes, there's all sorts of assumptions under the hood, biases, uncertainties that get overlooked, and maybe it's reification. Maybe it's something of a blurring of reality with the model, with model land. That is sometimes seen in climate change could do X, right? So such and such an impact in RCP 8.5, which is a highly unlikely scenario that has all sorts of rather extravagant assumptions built into it. But nevertheless, it propagates as sort of like what climate change could do. Do you get that sense as well? And if so, what can we do as science communicators, experts, academics, etc.?
Yeah, so in terms of the sort of seductiveness of the simulations, I think that because climate models are quite detailed, they produce very detailed visual output, which sort of looks very attractive. It looks plausible. It looks convincing. This is a plausible outcome. This is a plausible simulation of the future. And so actually then, yes, I think it becomes quite hard to separate that and say, actually, this is only a model and it has grid boxes. And we always smooth out the picture, don't we? You never see the climate model output in blurry squares with grid boxes. You see it all nicely smooth so that you've got contours, and the outlines of continents are always very detailed. So it looks like a map. And it's hard to believe that it's not a map. And so I think from the sort of public communication point of view, yes, it's easy for that to be misunderstood. And the uncertainty is extremely hard to visualize on a map. And it's hard for people to understand what they're seeing when you do try to visualize that uncertainty. And then I think also when you take the more quantitative information to quantitative decision makers, they will say, well, we need a number, and this model is what's able to give us a number. And maybe you can give us an uncertainty range as well, and we could probably use that. But the question of sort of unquantifiable uncertainties, actually, that doesn't fit with their decision making. And so there is always a push towards the quantitative, the definite, and the sort of visually attractive climate model outputs. And then you also mentioned follow the science. And I think that's an interesting one. And that's one where I do have some opinions about communication, because I think we have to be really clear that the science does not tell us what to do. It only tells us what might happen if we do X and if we do Y. And the decision about which outcome is preferable is one that implies value judgments. It's one that implies political positions. And it's one that we shouldn't claim is uniquely determined by the science. It's a perfectly coherent ethical position to say that you would like to burn lots and lots of fossil fuel and never mind what the future climate looks like. That's a value judgment that I happen to disagree with strongly, but it's a coherent value judgment, and we shouldn't say that it is precluded by the fact that the models project severe climate changes if we do continue to burn fossil fuels. Because I think if we do that, then you see what we have seen is that people then go back and they pick at the science instead of having discussions about values. So I would like to see more discussions about values and maybe not more consensus, but sort of allow the science to do its thing without being contaminated by all of that, And so one of my other points is that the science includes values, and it does. It invariably and unavoidably incorporates value judgments at every stage, from the decision of what to work on to the decision of how to represent different things and the kinds of interventions that you even consider representing in the models. But I think specifically that question of if we do X, then Y will happen, and if we do Z, then something else will happen, then we should allow people to have their differing value judgments about the outcomes without saying that that is determined by the science. So I don't like follow the science. I think it's a bad phrase.
A moment ago, I mentioned hidden assumptions in models, and I don't mean to imply anything nefarious. The modelers themselves can be very explicit about the assumptions of their model in academic papers, which then feed into the IPCC long reports and then up to the summaries for policymakers and then over to the news, the mainstream news coverage. And of course, subtleties are lost. In the case of climate change, one assumption that ended up being hidden I find quite instructive is mentioned in your book, and that's the assumption of large-scale carbon removal to achieve climate goals. And what's fascinating about that is in both the fifth assessment report cycle and in the lead up to the special report on 1.5 degrees warming, that was driven by the target. First by 2 degrees C and then by 1.5 degrees C. And the idea is, how can we get there? So it's sort of an opposite direction in a way from traditional climate modeling. If we do this, what will happen? It was, we want to end up there. Can we make it happen to get there? Can you say a little bit about how that happened and what the consequences might be, more importantly, what the consequences might be for our understanding of complex decision-making, such as climate change?
Yeah, so we're shifting here from a discussion about physical climate models to a discussion about the integrated assessment models of sort of economy and climate that inform decision making about different technologies and policies for, such as carbon capture and storage, carbon dioxide removal, different electricity technologies, energy supply, and all that sort of thing. And I suppose one of the interesting things here is the way that these models are typically framed around a least cost pathway. So they'll say, okay, we've got a target for 2100, which might be to keep things at 2 degrees or 1.5 degrees or some other pathway. And then how do we achieve that with the lowest cost to society? And so they do that by balancing the costs of energy technologies now and in the future. And that might include carbon dioxide removal or, anything else you can think of. And ultimately, the degree to which they are leaned on by the models, and there are several models and they're all slightly different, and they sort of prefer different technologies in a way. You can see that if you look at the outputs. But the degree to which they prefer one technology over another will depend on the kind of assumptions that went into that model, and in particular, the assumptions about price. So if you put carbon dioxide removal into your model at a price of $200 a ton, then probably not very much of it happens for a while. If you put it in at a price of $2 a ton, it'll happen straight away, and there'll be huge amounts of it, and it'll be the main thing used to meet the target. And if you're somewhere in between, there are sort of switchovers, when solar electricity becomes cheaper than coal, for example, then you see things shifting, and we do see that. And it's reasonable, it's correct, it's right to say that when one technology becomes cheaper than another, then the economic forces and the way that we work are such that it will then be favored and there will be more of it. So it's realistic in that sense. But obviously, we don't know what the future for these technologies will be because they haven't been developed yet, or they depend on future pathways. Maybe we have the technology, but we don't know what its price is going to be in 20 years' time. For example, you can see over the last 10, 15 years that estimates of the cost of solar energy have consistently overestimated, and it's consistently become cheaper than expected, which is great. And it's really good. That's really positive. And it helps the models to incorporate more renewable energy, and it helps us in the real world to do more renewable energy. But it shows that we are limited in the way that we make assumptions, even about a relatively well-developed technology. And so when you then take that to something like carbon dioxide removal from the atmosphere, the air capture technologies, which are really only at demonstration stage, and you say, could we scale this up to do hundreds of thousands times as much as we do at the moment? And how much is it going to cost? Well, that's a number that you basically just pick out of thin air. And, you could support a relatively low cost for it by being optimistic about technology and by being optimistic about research and development and scale up and investment. Or you could end up with a very high number if you say, actually, this is going to be technically difficult. It depends on economic cooperation. There might not be political appetite for it, et cetera, et cetera, et cetera. And where you end up between those makes a massive difference to what your model says.
So I guess one of the questions you have in your book that I thought was really interesting was this question of, is the model adequate for the purpose to which it's applied? And I mean, I'm most familiar with Earth system models, these climate models. What is their purpose? And are they adequate for it?
So this is a concept that's really stressed by philosopher Wendy Parker. And I mean, she's written a lot about adequacy for purpose. And I suppose the problem is that we want to put climate models to a whole range of different purposes. We want to use them to inform global climate negotiations. We want to use them to make local adaptation decisions. We want to use them for all sorts of things from the international scale right down to the individual scale. And so the question of whether the model is adequate for all of those purposes, you can't answer that in one sentence, because some kinds of decisions it will be adequate for the purpose of informing, and some it won't.
So I think we've already touched on this, but the basic approach of the climate community or the climate modeling community is to, every time they get a new supercomputer, they crank up the resolution and complexity of their model so that they can run it roughly the same number of times. So they can get 30 model runs complete in time for the latest IPCC report, so they can show off their nice high resolution results. Is that model of using climate models the best way to go about it if we're trying to address the kind of questions you raised there? Or should we be thinking a little bit differently?
Well, I mean, I suppose there's a sort of boring answer to the question and there's a more exciting answer. And maybe the boring answer is just to say that actually it makes our statistics difficult if we can only run it a small number of times. And perhaps it might give us the, in inverted commas, best possible information. But if we don't know what the range of uncertainty is, that's not very useful information. And so I think from my point of view, it would make more sense to be spending more of our computational power running multiple models and pushing the boundaries of those models, saying how far can we really get this to go before it does something crazy, than to put all of our computational effort into one model to rule them all. And maybe the more exciting answer is to say that I think what we need to do to make our statistics more valid, we don't need to say that we've got 20 models and they all say the same thing. Actually, what we want to know is that no model that we could conceive of making would give a different answer. It isn't actually any additional information to know that another model made in much the same way gives us the same answer. it would be really useful information to know that no other possible model could give us a different answer. And so what would be one of the things that I sort of put forward in the book that I would like to see, that I think is unlikely to actually happen, but would be really interesting, would be to push the boundaries much more and to say, actually, our ensemble of models shouldn't just be generated by tweaking the parameters of atmospheric fluid dynamics. We should be thinking about trying to incorporate models which are made from a completely different starting point. What about a model that began with ecosystems? Can we develop an ecosystem model to include a climate subroutine? Maybe in the way that we at the moment have climate models which have huge amounts of resource put towards atmospheric fluids and only a few subroutines towards ecosystems. Could we do it the other way around? I mean, I have no idea what it would look like. I'm not an ecosystem modeler, but I'd love to see what would happen if we got some ecosystem modelers to do it. And so we almost have an idea of it from integrated assessment models, because they are sort of probably large spreadsheets rather than the giant beasts that we have of climate models. But they're kind of giant spreadsheet models, and they include climate as a small subroutine. So that's an interesting counterpoint to the physical climate models, although the subroutine that we have for climate is derived from the physical climate model, so it's not independent. But what about a model that was based on human rights or, mental health? Could we develop a model of climate change that began from a completely different starting point? And what would that look like? And would we get the same kinds of information feeding into decision-making pathways? So it's a bit out there, and I don't know what it would look like. What about indigenous knowledge? What about if we set indigenous peoples the task of making a climate model? What would it look like? With the same function of feeding in, let's give it a purpose. Let's say to feed into international climate negotiations. What would it look like? Would it be comparable in some ways with the ones that we have? Or then you say, well, actually, maybe it would reject the whole system and say we shouldn't be doing it like this at all. Well, that's also really useful information. That's if we can put different forms of knowledge and different perspectives and backgrounds on the same platform and at the same level as the kind of knowledge that we have for those of us who've been trained in atmospheric fluid dynamics, what would we get?
I guess this is kind of a question of, to some extent, there's a supply and demand and a history that shapes the problems with any societal demand for, we want to know, is the climate changing? So there's certain approaches that are suitable for that. An ecosystem-based approach or an indigenous knowledge-based approach. There's different ways of questions. And I guess I wonder, because this is something you talk about in the book, is these framings for problems that we've inherited. I guess I'm just wondering, could we have the demand for these things? Is there just some ways of reframing the problem? Because I guess there's infinitely many ways of doing stuff. Only some of them are useful.
Yeah, it's also about sort of our hierarchies and power structures that exist and the kinds of people and organizations and corporations that have power to influence these processes and the money to be able to fund scientific research. Who is it that wants this kind of information? Well, the people that want the very detailed quantitative information are highly numerate corporations. They are things like insurance, the insurance industry, reinsurance, large multinationals that are able to kind of experience climate risk as a probability distribution. Whereas if you are a farmer living on one field in sub-Saharan Africa, you don't experience a probability distribution. You experience the thing that happens to you. And so it doesn't really matter to you in that sense what the probability distribution is. It matters what happens to you. And so I think you can't give that user, for different users, different kinds of information are adequate for the purpose of informing them how they should act. And the kind of information and the kind of way that models and climate models and weather models have been developing is to provide information for highly numerate, highly quantitative, highly connected, and probably also relatively geographically dispersed users, rather than necessarily for those with less money and less resource.
I guess turning to perhaps a bit more of a controversial case, I think you cover in your book, COVID was a tricky one. This is one of the ones where I think there's very different framings of the issue. Is this about number of people dying, or is this about economies and freedoms being curtailed and destroyed? How have models played out in that domain? And what does some of the political reactions to it tell us about the prospects for doing things better?
Well, I think this illustrates some of the problems with the follow the science idea, because, you can generate a model which says if we don't wear masks, then hundreds of thousands of people will die or whatever. People can legitimately differ in their opinion of the degree to which the pros and cons balance out. And so some people put much more weight on individual freedom and social contact and all the rest of it. And some people put more weight on the morbidity and mortality. And I think people tend to come to it with a very fixed opinion and a very preconceived idea of what the obvious right answer is here. And maybe one of the messages of the book, I hope, is that if we can accept that we are all working from the same facts, but science, which is to a degree subjective, and value judgments, which may be completely different, then we have to talk about the value judgments as much as we need to talk about the science. And so I think COVID has kind of illustrated that really clearly for me. And it's really disappointing to see the way that things have become polarized and the way that both sides, that there's to a degree people sort of looking at the science and wondering whether they agree with the science, trying to pick holes in it, amplifying narratives of disagreement and distrust. I think this is really socially corrosive. It makes life really hard for scientists who, in general, are absolutely doing their best, but it makes life hard for everybody living in a society where people are so sort of knee-jerk skeptical of anything that doesn't conform with their pre-existing narratives. And so you see that in climate as well, of course.
So we like to end on a hopeful note, but I'm going to pose it more as a question. With increasing computational power and the availability of data, the attractions, power, and capabilities of model land are going to increase and increase. Does that make you hopeful about the future, or are you worried?
I'm worried. But I think I'm worried because we seem to be going towards this more quantitative domain, and where people just shout, follow the science, and then try to get their model to steamroller everybody else's opinions. I think that is extremely negative. And perhaps the contribution of my book, and what I hope I've sort of explained, is that we need to be talking more about value judgments, more about the value judgments in the way that they come into the models, and more about our value judgments over the potential outcomes. Because it feels to me that, for COVID and climate and all sorts of other applications of complex modeling and thinking about the future, actually what we need is a vision of a positive future that everybody can work towards, rather than be constantly holding up worst case scenarios derived from models and say, oh, we need to avoid this. Oh, now we need to avoid that. Oh, now we need to avoid this. Actually, if we can have a shared discussion about values, and a positive discussion where we can agree to compromise, and I know that's difficult in today's society as well, but thinking about how we can work together rather than pushing each other apart, then I think the models can be incredibly helpful and incredibly informative. There is a huge amount of useful information in these models which can genuinely help to support good decision making in the future, and can help us to achieve a vision of what we want society to be like. But we have to have that discussion about values first, and not expect that the computer is going to solve all the problems for us, because it isn't.
And your book, Escape from Model Land, is now available in all good bookshops, and a great way to get into some of these questions and to think more about Model Land as it comes to swallow up more of our world. Thanks for joining us.
Great, thanks. Nice to be here.
Well, thanks for listening. Please rate or review us on Apple Podcasts and elsewhere, and consider supporting us on Patreon. That's patreon.com/challengingclimate.